Well, welcome this afternoon to this program. I'm Ginny Stimson, the chair of the Low Vision Hearing Challenge Committee. And we have been trying to get Dr. Van Gelder back here since he was here in January, and he gave us that excellent talk, if you remember, showing different operations on the eye and telling us about the latest things that were happening. And he offered at that time to come and tell us about the research that was happening. So I have quite a description to give for him, but if you were here before, you don't need to hear any description. You know how much he knows. But Dr. Van Gelder earned his BS, MD, and PhD from Stanford University. Following internal medicine internship at Stanford, he completed his residency in ophthalmology at Barnes Jewish Hospital at Washington University in St. Louis, and his medical retina and uveitis fellowship at the Barnes Retina Institute. Dr. Van Gelder remained on the faculty at Washington University from 1999 to 2007. His research has continuously been funded by the National Institute of Health since 1999. His laboratory has been at the forefront of two fields: non-visual photoreception and pathogen detection in uveitis. I had to look that word up. The uvea is a lining of the eye, and it's itis means swelling, right? So, okay, we got that, okay. He has published over 100 papers and book chapters, including papers in Science, Neuron, Nature, Genetics, and Proceedings of the National Academy of Sciences. Since 2008, Dr. Van Gelder has been the Boyd K. Busey Memorial Chair, Professor, and chairman of the Department of Ophthalmology at the University of Washington here in Seattle. So he went from Washington University in St. Louis to the University of Washington in Seattle, which my father did too. He is director of the Roger and Angie Corrales Johnson Retina Center. He is adjunct professor of biological structure and of laboratory medicine and pathology. Nationally, he is past president of the American Academy of Ophthalmology and serves as editor-in-chief of the journal Ophthalmology. Dr. Van Gelder is an active clinician, scientist, and teacher. He has published over 200 peer-reviewed papers and has continuously been funded by the National Institute of Health since 1999. He sees patients with ocular inflammatory disease 1 day per week and divides his remaining time between research, teaching, and administrative duties. And part of what he does is to come to the community like this and share about the research so that we know about it. And I think it's wonderful to have you back. We welcome you.
Well, thank you so much, Ginny. It is a pleasure to be back again. I really enjoyed my opportunity to be here in January. The only challenge is I'm told I'm a tough act to follow, and now I have to follow myself. So those of you who enjoyed the first talk, I hope you enjoy this one. This one's going to be a little bit different. We're going to talk about the research going on at UW, and in particular, the things we're doing to try to instill hope in the community that some of our causes of blindness will be addressable and treatable in the foreseeable future. I want to start out with a nice picture. So in 2007, right before I moved to Seattle, we had a meeting in Paris, an eye meeting. And one of the perks of being in academic medicine is you travel like a rock star and you get to go to meetings all over the world. In this particular meeting, I had a free afternoon, and a friend and I ambled down to the Musée d'Orsay, where they were having a temporary exhibit on the first photographs, the daguerreotypes of the 1850s. And this particular picture from 1850 really caught my attention because if you look carefully, it's a lovely picture of two sisters. But if you look at the sister on your left, she has a cataract, you can see that right here, on her right eye. And this is probably the first picture of a cataract. Since photography was only invented in the late 1830s, I'm not sure there were any pictures before then. We almost never see this anymore. You don't see someone on the street with a cataract like that, but it was quite common in the 19th century. So what is a cataract? Cataract is when the lens of the eye, which is the component, let me see if I have a pointer here. So here's the lens of the eye, sits right in the middle of the front part of the eye. It does about a third of the focusing of light rays onto the back of the eye. And as we get older, it gets cloudier. In fact, let me take a poll. I did this last time. How many of you have had cataract surgery or will admit to it? Let's make it easier. Who has not had cataract surgery? 1, 2, 3, 4. Yep. So I'm preaching to the choir here. You guys know what cataract surgery is all about. What you may not realize is that the procedure that you had, presumably a few years ago, where you came in and it was topical anesthetic and took 20 minutes, it hasn't always been that way. And if we go back in time to about 1100 AD, the technique of choice was called couching. And remember, in this era, we didn't have anesthetics, we didn't have microscopes, we didn't have much. We did have sharp sticks and we had fire. And so what a couching surgery was to take a piece of basically a knife blade, put it in a fire to heat it up, and then plunge it into the eye and try to push the lens out of the way and push it off to the side. And you could imagine this was not a popular surgery. This is from 1500, a lovely picture of the chair that you went into before your cataract surgery, right? So that you couldn't move your arms or your legs. And even here in 1850, as anesthesia is starting to come into vogue, you have this two-person procedure where one holds the head still and the other one goes and couches. Gloves were not a thing in the 1850s. So the odds of someone having vision after the surgery was pretty low. And the odds of losing the eye was pretty high. And that's why that young lady said, you know what, the other eye works. We'll leave well enough alone and not do cataract surgery. You know, and contrast that to today, where I'm going to show you a sort of super high-tech, well, I may show you a super high-tech sound here. Let's do that. Okay. Right, so what we're looking at here is a future cataract surgery. And this is a femtosecond laser. So this laser is actually manipulated with a computer here. And the laser does the cutting. So you'll see the surgeon is setting up where he or she wants the incisions to be made and what part of the lens to be incised. And then once that's all set up on the computer, you basically hit a little foot pedal, and you'll see in a second that right here, this takes an image of the front of the eye so we can see where the lens is with an OCT. And then once you've calculated exactly where you want the cuts to be made, in cross-section, the laser now will adjust the depths of the incision. So you just draw where you want the cut made, and this laser, which cuts to an accuracy of about 2 microns, and you can see it starting there, and the bubbles are where the actual laser energy has gone into the eye to break the lens up, and you can now see that's an incision being made on one side for the instruments to go in, and the incision being made on the other side. So that's about half of a cataract surgery, and it's been done without anyone touching the eye to this point, all with lasers. We don't do this type of surgery yet at UW. It's not clear that the benefits of it justify the very huge cost of the lasers. We can still do these surgeries pretty well, but I would guess 10 or 15 years from now, this is how most cataract surgery will be done. And you can see the other steps of the surgery happening here, but for the sake of time, I won't take you through the whole surgery here, but it really is about a 5-minute procedure after the laser has done its thing. So we go from a very common blinding condition that basically meant getting strapped into a chair and having a hot poker stuck in your eye with a very small chance that you'll see, to something that now is a 20-minute procedure under local anesthetic. It's no worse from your perspective than a dental cleaning, and you come out of it with vision. That is the goal. And that's what we want really for all people with eye problems, is to get it to the point of cataract surgery for a level of solution. Now, if we think about the reasons that people go blind, and we talked about this in January, we have several. We have cataracts, as we just mentioned, but we also have macular degeneration, which is shown here, diabetic retinopathy, and glaucoma. And those are our other major causes of blindness. There are many, many others: corneal disease, retinal detachments, lots and lots of macular holes, all sorts of others, but these are the big ones. And all of them are in the retina. So the retina, which we talked about last time a little bit, is really where the magic in the eye happens. It converts the photic energy from photons from artificial light or the sun into a chemical signal, which then is converted into an electrical signal and goes out our optic nerve to the brain, and that's how we see. The retina itself is about the width of a piece of Kleenex. It's a very delicate structure. It has 3 cell layers within that Kleenex width. And because it is such a delicate and such a specialized tissue, it is very prone to injury and very prone to disease, and it is the major cause of why people go blind now in this country. And in fact, if we look at the causes of blindness in industrialized world, that is Western Europe, Japan, US, it's about half macular degeneration, it's about a third glaucoma, and it's about a third diabetic retinopathy, give or take a little bit. And there's a little bit of other things, 10% in there, I should say a quarter, less than a quarter of glaucoma and diabetic retinopathy. So age-related macular degeneration is our big problem, but these others are also significant problems as well. And the problem is not going to get better with time. Thanks to modern medicine and people living longer, that gives you more opportunity to get macular degeneration. And if you're age 80 or older, which I suspect a few of you are in the audience, your odds of having signs of macular degeneration are 1 in 3. And your odds of losing vision from macular degeneration are 1 in 10. So this is pretty prevalent stuff. And if we did the show of hands, I'm pretty sure a few of you have macular degeneration or signs of it, given the size of the audience here. Now, what are we doing about this, and a little bit about what UW is doing on the research side? We were very fortunate about 5 or 6 years ago to get a wonderful gift from Angie Corrales Johnson. Angie is the widow of Roger Johnson, who was an ophthalmologist in town. And again, I would guess 1 or 2 of you saw Dr. Johnson as a patient, because when his practice was sort of at its peak, he saw probably 10% of the population of Seattle back in the day. I'm seeing some nods there. Wonderful, wonderful man. He passed away in 2007. But Angie has been very, very, very generous to us and provided funds for us to set up really a world-class research and clinical center, which is at South Lake Union. And if any of you are out for a stroll and head up that way towards Dexter and Mercer, walk up through the courtyard between the 2 buildings. It's an architectural gem in Seattle, with this beautiful fractal window wall and this nice bridge connecting the 2 buildings. The main thing from our perspective is that those buildings allowed us to build a clinic in the building on your left, which looks something like this in outline, which allows us to see patients, and we see about 10,000 patient visits a year for people with retinal disease at the center now, but it's connected on the right with 30,000 square feet of research space, which makes us one of the largest research departments in the country. And in fact, in the last NIH rankings of funding, UW was number 3 in the country of the 120 departments of ophthalmology for research funding in vision. That is National Eye Institute funding. So we have a really robust program. Space is great, but it's all about the people, and these are the folks who work at the Retina Center. It is a fantastic group of PhDs, MD PhDs, and MDs who are all dedicated to trying to make the future with respect to retina disease similar to where we are for cataract now. So what I'd like to tell you about in the next few minutes are little vignettes of the research. Any one of these is easily a 1-hour talk if we go into the detail. So I'm going to give a very high-level view of the type of research we're doing, and then when we get to questions, happy to take questions about this or anything else related to ophthalmology. So our Retina Center has 4 pillars of research. We designed it around 4 areas: advanced imaging and optics, computational ophthalmology, we'll talk about what that means, translating the therapeutic pipeline, that means getting drugs to people, and vision restoration, which I think is the most science fiction-y, but also in some ways the most exciting, because we're actually getting to a point where these things are becoming a reality. Now, those of you who have been to the ophthalmologist in the past few years have probably had one of these scans done. This is called an optical coherence tomogram. And it's a very low-power infrared laser that scans your retina and then takes the light beam that's bounced off the retina and interferes with it. It takes the interference pattern and does a mathematical transform on it, if there's any engineers in the audience. So it does a Fourier on the reflected wave, and based on that, you can reconstruct what the retina actually looks like at a cellular level. That is, you can see the individual rods and cones and ganglion cells in the retina in a live person in real time. And that has transformed our ability to diagnose things like macular degeneration. If any of you are getting injections, for example, in treatment for macular degeneration, you probably get one of these scans every single time you come see us, because this is how we make our decision as to whether you need more treatment or not. It's a great technology, but Ricky Wang, one of our faculty members, who's the George Kren Professor of Ophthalmology as well as Professor of Bioengineering, thought we could do more with this technique. So he hot-rodded that machine, that OCT machine. Initially, the one that we had could scan at about 20,000 scans a minute. And he took it up to 150,000 scans a minute, because he's a really good engineer. And it turns out he could scan the retina so fast, he could scan it once when the heartbeat was in systole, and once when it was in diastole, that is, when it's beating and silent. And then he took the two pictures and subtracted them. And you know what he found? A complete map of all the blood vessels of the retina. Unbelievable. These are the capillaries. This is his own retina. This is called the fovea. That is the dead center of the vision. And now with this level of technology, we can see every blood vessel in the retina. And so if you have retinal vascular disease, occlusive disease, we can diagnose it and potentially treat areas, for example, with laser that are ischemic, because we can see them. No dyes, just basically it's more data from the same scan we were doing anyway. Taking this even one step further, Ram Sabisan in our department is the George Kren Professor of Ophthalmology, where Ricky is the chair. And what Ram has done is to take a technique that was developed for the Hubble telescope. Those of you who are astronomy buffs know that when the Hubble went up, it didn't work very well. And they had a problem because the mirrors were slightly deformed and they couldn't get the images that they needed. Turns out you can fix that in software. So there's a technique called adaptive optics where you make a mirror that deforms very precisely, and you make it deform to exactly counter whatever optical aberration you have in an optical pathway. Great for astronomy, but Ram thought, why don't we use this for looking inside the eye, where we're also limited by optical aberration? And so when he did this OCT, this retinal imaging, and was able to apply adaptive optics to this, he got an image that looks something like this, which allows you to see every single cone in the retina. Each one of these little white dots here is one photoreceptor. You have 100 million of these in your retina, and we can see each one. Now, why is this useful? Well, what he was able to do is, for example, this is someone looking at the letter E here on the eye chart, and you can actually see that in real time, exactly what they're looking at. You can imagine we can map out now exactly where your vision loss is based on looking at the individual cells. And to that end, he was able to do an experiment, really remarkable, where he froze the image. That is, he put a tracking device on here so that now you don't see all that scatter. He's just got this one cell sort of in his pinchers. Even though the eye is kind of moving, everyone's eye moves a little bit. And what he can do with this now is he can stimulate that one cell with a laser. And then he can ask the patient, what do you see? And that means that we can tell that this cone is a green cone, and this cone is a red cone, and this cone is a blue cone, because you put a laser on one cell and say, I see blue, I see green, whatever. Why is this important? Well, as we start to do drug trials for macular degeneration, it's a slow degenerative process, and current trials take upwards of 5 years to finish to say, yes, we had an effect, or no, we didn't have an effect. But if we can go back to the same spot on the retina and test it over and over, we can see if there's an effect in 6 months or a year, where it would have taken us multiple years before to figure out if something's working. So really accelerating technology to help us get treatments to patients faster. Computational ophthalmology. So all of you are aware we are in the era of big data, and computational methods allow people to analyze things that we couldn't possibly do before. So Aaron Lee is a vitreoretinal surgeon. He's also a computer scientist in our department, and he and his colleague and wife, Cecilia Lee, have applied these big data approaches to both understanding the epidemiology of disease, but also the pathophysiology of disease. And what do I mean by that? This is an example, and again, I can only give you a little taste of this at the 30,000-foot view, but those of you getting shots for macular degeneration, most of you are going to do very well over a long period of time, but not everyone. And there are some people for whom a particular drug is not working, or it has stopped working and the disease progresses. Wouldn't it be nice to know who those people are early on so that you can switch quickly? And what Aaron and Cecilia worked out was a calculator that you come in each visit and you put in the data based on that visit, and using artificial intelligence, it predicts whether you're in the high-risk category for the drugs to stop working or you're in the category where it's likely they'll continue to work. And if you're in the high-risk group, we see you more often and bring you back and make a decision to change drugs or go to a different therapy. In aggregate, they've also been able to do huge data studies. This is the burden of blindness in England, and they had access to a very large English data set, essentially showing that these new macular degeneration treatments have halved the burden of blindness from macular degeneration in the UK. But I think more exciting are some of the applications that they have applied to deep learning. And I'm sure all of you have been following the news about artificial intelligence and ChatGPT and large language models and all of that, because it's a very, very hot field, and we're right in the middle of this. There's a category of artificial intelligence called foundational or unsupervised learning models. And these are pretty amazing models where you essentially just throw a lot of data at a neural network, and it will kind of figure out what's normal and what's not normal in a big set of data. Unsupervised, you just throw all the data at it and you say, show us what's not regular here. And so when Aaron and Cecilia did that for retina pictures, they asked the computer to color code the part of the picture that didn't look right to it. Now, we didn't teach it anything about the retina or OCT, nothing. We just threw a million OCTs at it, and it puts up this little heat map, and it tells us where the pathology is now. So we basically can use this as an assistive tool to say, you know what, your retina looks okay, but we do see this little spot here we need to keep an eye on, or that might be the beginnings of some macular degeneration or diabetic retinopathy. And this is assistive AI. I think a lot of people worry about their job being taken by AI. I'm not too worried, but I sure could use the help. And I think this sort of approach to say, here's a computer program that will look very carefully at the data and help me, help you make decisions is really where we want to be going in the future. So let me tell you a little bit about stem cell work, and this is getting into translational pipeline. This is the work of Jennifer Chow, who's an associate professor, is the Berge professor in our department. Stem cells, there's a lot of buzz around stem cells, right? It's a very exciting technology, and particularly in the eye. In the 2000s, 1990s, 2000s, stem cells also had some ethical challenges because they derived from embryonic products. Those days are long gone. So when we talk stem cells now, we're talking inducible progenitor stem cells, which you make out of your own blood or cheek swab, or there's no embryonic tissues involved anymore. These are IPSs, or inducible progenitor stem cells. And the way I like to explain stem cells is it's kind of like education. If you look around this room, there's probably a few of you who are attorneys and a few who are doctors. And when you were all in kindergarten, all of you could have been any of those things, but your pathway and who you were around in your education made some of you go to med school, and some of you go to law school, and some of you go to business school, and some go to nursing school, et cetera. But in kindergarten, many of you could have gone anywhere. Well, what stem cell is really that kindergarten stage where you can become anything. You can become a photoreceptor or a ganglion cell or a skin cell. And the way the IPSs work is it's a little like that movie Billy Madison. you take an adult cell and you actually de-educate it so that it becomes a kindergartner again, and then you tell it this time you're going to go become a retina. And what we can actually do is take blood or cheek swabs from a patient, grow them in a dish, give them the proteins that they need to become a retina, and lo and behold, after a few months in the dish, we get these beautiful structures growing, and this is an immunohistochemistry stained for proteins that are specific to the retina, where we have what we call an organoid, a retinal organoid, that looks a lot like a retina growing in a dish all by itself. So that's a pretty cool Frankenstein experiment, but what use is this? And the answer is, if we now take cells from someone who's got a particular disease, let's say a genetic form of macular degeneration, we can now grow 10,000 little copies of your retina in a dish. And we can ask the question, for example, if we go down the street to Bartell's, actually I shouldn't say Bartell's because there's no longer Bartell's down the street, sorry. If we go to Walgreens down the street and we say, give me one of everything. I want one drop of every drug you have on the shelves. And now I go back to my 10,000 little retina copies, and I put a drop on each one of those copies, and I ask, is there any drug that I could prescribe you today that would slow your degeneration process? The answer, it turns out, is yes. There are several that we've found in screens. And I won't go into the details again, except to say we have a clinical trial starting, actually now it's enrolling, for a drug that is commonly available on the shelf that we think will slow retinal degeneration. Super, super exciting. And we're targeting a slightly different kind of degeneration called retinitis pigmentosa with this first trial. But the data are there that in the dish and in animal studies, this very commonly, it's actually disulfiram, which is antabuse, which is normally used for alcohol abuse, but it turns out it slows degeneration in animal models and in vitro. So this is an approach really to leverage this technology so that we can try to find drugs that we can use today as opposed to having to develop brand new drugs that can take a decade or longer to come to market. So finally, let me talk a little bit about vision restoration. And this is really the most science fiction-y work of the whole bunch, and it's the work that my own lab has been doing for the last 15 years or so. And one of the perks of being a chairman is that I can do stuff that's a little riskier because my boss isn't going to tell me to stop. So I've taken advantage of that and kind of gone out on a limb here and done a few things that I'd probably not tell my junior faculty to work on, but I figure if it doesn't work for me, I still have a day job. So there have been a number of approaches over the past few years to try to restore vision when it has disappeared. And the reason that we lose vision in diseases like macular degeneration and glaucoma is because the cells in the eye die. The goal then is either to bring those cells back or make other cells function like the cells that we've lost. So we can think about stem cells as a replacement therapy where we grow some cells in a dish and then put them back. We can think about electronic prostheses. We're not doing a lot of work in this field. I think the idea of putting a chip in the retina, although it's been done, has some real challenges. It's hard to get a big piece of hardware inside an eye and get it powered and everything else, but people are working on it. There is work on gene therapy, which I won't have time to talk about today. And then there's a small molecule approach, which is what my lab is doing, which I'll tell you about. But let me tell you a little bit about stem cell replacement first. This is work from, again, Jen Chow's lab. And this is an immunohistochemistry of 3 different retinas being grown in a dish, that organoid that I showed you before. One of them is actually human tissue that was taken from an autopsy. One of them was from an embryonic stem cell, and one of them was from an inducible progenitor stem cell. And the point of this image is that you can't tell them apart, and neither can we. We can basically grow this layer of the retina, the pigment epithelium, so that it looks exactly like autopsy tissue. Now, can you transplant it? And the answer is yes, and Tom Ray in our Department of Biological Structure has been at the forefront of transplanting these stem cells back into the retina. For those of you who are not red-green colorblind, this is a cone that came from a donor where it was labeled genetically and put into a mouse retina and allowed to grow. And you can see that that stem cell-derived cone is very happy in the middle of the retina and functioning. in that space. So the first big experiment, whoops. Not sure why I'm not getting forward here. Let's try this. Come back over here. There we go. Yep, sorry about that. So Jen and Tom did an experiment a couple years ago where they took about 1 million of these iPS-derived stem cells, genetically labeled them with a green fluorescent protein, and then injected them here. And this is the superior retina of a macaque monkey. And this was the first experiment in the world to put human-derived cells, iPS cells, into another primate as a transplant. Oops. And this is, oops, there we go. So this is what the experiment looked like. They took a picture of the monkey's eye every 3 months, one with regular color, one with a filter that only showed the green. That's the transplanted cells. And what you can see immediately is, number one, the green doesn't go away. So at 3 months, those cells are perfectly alive and happy. But what I think you can also see, those of you who can appreciate this, is that by the 3 months, we have these little fibrils here. And if you look at the composite picture, they're going right into the optic nerve. These are axons of new ganglion cells that are making a beeline for the brain to try to connect. So we take this as a very positive sign that stem cell-based technologies are feasible. Have we cured anyone's blindness with this? No. Are we ready to go into humans yet? No. But did it pass the milestone of saying it's plausible? Yes. So I think there's potential here. So I also have to say there's a lot of hype around this, and I would be careful when you're out in the wild world and hearing about stem cell things. Just like last month, there was a big press release on a, quote, eye transplant that came out of NYU. Yes, they did an eye transplant. Could the patient see? Not a whit. They put basically a non-functioning eye in someone, cosmetic surgery. But if you just read the press release, you would think they cured blindness by an eye transplant. And I got calls, hey, am I a candidate for an eye transplant? And the answer is absolutely not. Similarly, you will see stuff like that for stem cells. So this surgery helped blind women regain vision, retinal stem cells, is overhyped right now. We can't really bring back anyone's vision yet. There's 2 clinical trials on retinal pigment epithelium stem cells that are ongoing. Results have not been posted yet, so be careful of the hype. And the reason to be careful of the hype is that stem cells are very loosely regulated in the US because it's your own tissue going back into you. The FDA can't really get involved in regulating this that tightly. And there was a horrible, horrible case in Florida of 4 patients who went to a stem cell clinic where a nurse injected their eyes with stem cells that were derived from the patient's body fat. And this is what happened to their retina. They were rendered blind, completely blind by the stem cell injection. So, so when I show our results with stem cells, I want to make sure I temper this to say, in the lab, encouraging, not ready for human prime time, and don't let your loved ones have any stem cell procedure done to their eye out in the wild world. These are technically legal, but they are unethical to do, and they are very dangerous. So caveat emptor. All right, so the last bit in the talk is really talking about our small molecule approach. And this is work we've been working on with our colleagues from UC Berkeley and now University of Pennsylvania. And for the scientists out in the audience, what we have is a light switch that a chemist named Dirk Trauner put on a drug for us. The light switch is called an azobenzene. It's 2 benzene groups with a double bonded nitrogen. And this is a food dye, by the way. You guys have all eaten pounds of this in your life. It's a red food dye. But the magic of this particular molecule is that when light hits it, particularly blue light, it isomerizes. That is, it goes into a kinked or cis conformation, whereas in the dark, it's in this trans conformation. And what we think happens with this, and I should mention, if we put this on a retina that is blind and subject that retina to light dark. This is before we treat it, and you can see there's no response to the retina to the light and the dark. But after we put the compound on, you can see now every cell fires in the light. And these are the ganglion cells of the retina, which don't die in macular degeneration or retinal degeneration. So the idea is that the drug basically comes in, finds its target, which is a voltage-gated potassium channel, it attaches, and now if we hit it with one wavelength of light, it goes into that kink conformation and the channel is open, and if we hit it with another wavelength, it closes. I basically showed you that before. So we can really turn these cells on and off then and make them fire with light, even though there's no rods or cones left in the retina. So we initially tested this in, take that away again, in mice. And we took blind mice and we injected their vitreous with a little bit of the compound. This is the same mouse you're going to see before and after the administration of this drug, just a couple microliters. So you'll see the light go on. This is under infrared, and the lights go on here. And you can see nothing's happening in the before, but in the after, you can see this pupil starting to come down. And that suggests that a signal is getting to the brain that the brain can at least interpret in this otherwise blind mouse. So the question we've had for years now is would this work in people? And I'm very happy to share with you data that I only shared at our Academy meeting in November. So this is really hot off the presses. This is a month old. Working with a company called Kiora, and I have no stock in Kiora. They don't pay me as a consultant. I have no conflicts of interest. They're just using our technique to try to get it to patients. We started a clinical trial. Oops, I'm missing one slide there. To inject this compound into the eyes of 6 people with profound level of blindness. 3 of them basically couldn't see light or dark. And 3 of them could basically just see a hand moving or maybe count fingers to see what would happen. For the patients who couldn't see light or dark, we first saw whether their ability to sense light and dark would improve. And what we saw is from day 2 to 29, and this was a single intravitreal injection of the compound into their eye, they basically had a tripling in their odds of being able to tell whether they were in light or dark or not. We also looked at the patients who had better vision to begin with, and we did a test with them called a rudimentary vision test, which is sort of like an eye test for people who can't read the big E on the eye chart. And again, we saw that after a month, their vision improved substantially from sort of barely being able to see a hand moving to being able to count fingers. Their visual fields improved, their ability to navigate a maze improved. So by day 14, they were able to make their way through a brightly lit maze that they weren't before. And we did MRI testing with these subjects and looked at whether their brains were reacting to the light stimulus. And if you look at this one, this was a patient who couldn't see light or dark at all. At baseline, we flashed lights, and you can see this is glucose utilization, almost none. But 2 days after the injection, there's a big signal now in the occipital cortex suggesting that the brain is responding to a light signal that the patient couldn't see before. And then by day 29, that fades back again. And in the subject who could see a little bit, and you can see some signal at the start, again, 2 weeks in, that signal is enhanced in that subject. So all of that is nice data, but what I really wanted to know was, what do these people see when we do this? And we did this study in Australia because the regulatory environment, frankly, is easier for us to do that. Their FDA is willing to allow small studies like this, where our FDA has much more onerous requirements that make it very difficult for small groups to try to develop drugs. And so we did this in Australia, and I want to play 2 videos for you of subjects who were in the study. Now, I apologize that they do have pretty thick Australian accents, so that some of you who are hearing impaired or can't hear an Australian accent may have a little difficulty. But if you can see, I have subtitled them so you can read this if you can't quite understand the thick Australian accent. So let's do the first one here. This is a gentleman who couldn't see anything before.
So before the study, I had no light perception whatsoever. And so, you know, at the start of the study, I had a couple of MRIs, and while I was there, and they flashed lights there, and I saw absolutely nothing. 48 hours after the drug, I had another MRI, and I think that was the first sort of OMG moment to say, what, I can actually see flashing lights. and you know, that was an amazing experience, to something that I haven't done for quite some time. One of the other times, I think, over the study, that was yeah, a moment that you go, this is working, was I was laying in bed in a relatively dark room with my wife, and she pulled out her phone, and I just turned to her and said, "Can you see? Are you using your mobile phone? Because I can see that the screen's on." And yeah, it was absolutely a definite do it. And I asked her, you know, "Can you turn the screen off and turn it on?" I'm going, I can see that when it turns on and off, and I can very much see the direction of the screen, the shape of the screen, and it was yeah, a really amazing moment from this study.
So that was the first gentleman who had no vision, and we clearly brought back some light perception for him. The second one was a woman who had some form vision but was legally blind, and this is her experience, which is a little different. Let's see there.
We walked to the supermarket at night time, and I walked into the supermarket and I thought I was in a sci-fi movie. I'm looking around, and it was just bizarre because we're of course in the chocolate aisle. I could see everything, and I could see every individual item, which I wouldn't have been able to do at night time with all the spotlights and stuff. And I could see every item, every block of chocolate, you know, all different colours. But the things that were bright were really bright, and the things that were darker were really dark. So everything was so itemised, and you know, I thought, you know, Dr. Spock was going to be the checkout chick. It was just, it was such a bizarre experience, but a good one. So that was a really good experience I had too.
So we're starting to try to understand why these people have the experience that they do. We've restored light sensitivity to the retina, but we think it's speaking to the brain in a slightly foreign language, because these drugs don't recapitulate the normal signaling of the eye to the brain. They co-opt it with an on-off sort of code, and this is the brain making sense of that. And I think this patient felt it helped her with higher contrast, but it didn't. It's not the native vision. And so a big part of my lab's work now is to try to make an assistive device that will, you know, be sort of the virtual reality headset that will translate the world into a signal that will be more like the native vision. So what does success look like? Well, for us, this is our WOW board at the Eye Institute. These are all patients writing nice notes to us that they've appreciated our care, and that is a big measure of success for us. This is a measure of success. These are fake news headlines of Seattle researchers successfully restore vision to blind woman, and blind patient sees again in Seattle. It's happening in Adelaide, but I'm hopeful that the next step of our study will be able to bring it back here to Seattle, and that's, we actually just today had a nice phone call with the FDA about what it will take to bring these small molecules back to the US so that we can do clinical trials here. What does failure look like? I think you guys will recognize what failure looks like, because many of you grew up at a time when these were still out there, and you think about polio. What if we had not had a polio vaccine? And we still had wards of the hospital full of iron lungs and kids being respirated. If we're still doing what we're doing 50 years from now for macular degeneration and glaucoma and diabetic retinopathy, that's failure. You know, even though we have some treatments, if people are going blind, it's equivalent to saying, well, you know, we have ventilators for polio, so we've taken care of it. Not even close. So our goal is really that this is not our future, but our future is that these diseases, again, become like cataract surgery, where you don't lose sleep, that you're going to go blind from any of these diseases. So I hope that's been at least an entertaining little run through some of the research that we're doing at UW. We do this because we serve you, and we are a state institution. We're right here in Seattle. Many of you I know get your care with us already. It's good to know what we're doing besides our just general care. We're also looking for partnership opportunities, and to be quite frank, this research is expensive stuff, and we have a lot of support from the government to do this, but it's not enough to support all of the research. And so we've been very grateful for donors like the Kren family, who I mentioned, the Berge family, Angie Corrales-Johnson, who have provided philanthropic support to help us serve you by bringing the future a little bit closer. If anyone is interested in the work that we're doing at a greater depth than what I was able to do today, we do lab tours regularly. And come on over to South Lake Union, and we're happy to guide you around the labs, let you see all the stuff up close and personal, and talk more about our research, because we love to show you what we're doing, and obviously we're always looking for opportunities to help our community. So with that, I will finish, and I am happy to take some questions. By the way, if anyone is interested in talking more about coming down to visit with us, Kathy Riley and Michelle LaPierre are both from UW Advancement and are front and center here, and would be happy to talk with anyone after the talk as well. So questions? Jack?
Thank you. Oh, your work is obviously mostly focused on the retina. Mm-hmm. Any progress in optic nerve?
Yeah. Well, you know, the optic nerve is technically part of the retina. And that stem cell experiment that I showed with the transplant is really an optic nerve experiment, because it's regrowing those fibers were optic nerve fibers. So yes, it's part and parcel of the stem cell work. The small molecule work, unfortunately, doesn't apply to people who have lost their optic nerve, because there's no communication link between the retina and the brain. And so we can make the retina light sensitive again, but there's no way to get that information to the brain at this point. So we're really focusing on retinal degeneration for that work, and stem cell work more for the optic nerve regeneration piece of it.
I get treated fairly regularly with Dr. Bui with macular degeneration and so forth. So, and I'm always amazed by the fact that I wait for her to put that needle in the eye and I can't feel it. You know, it's she managed it's done before, which is pretty amazing technology in itself in terms of just anesthetics. But tell me what she's doing. Once again.
Yeah, so when she treats you for wet macular degeneration, aside from putting some lidocaine on your eye so you don't feel any of it, the drug is, well, I should ask you which drug. Is it Avastin? Is it Lucentis? Is it Eylea? Eylea. So Eylea is it's a synthetic drug that's made up of a receptor for a hormone, basically, called vascular endothelial growth factor, that's been molecularly fused to a piece of an antibody. So it's called a chimeric receptor. And it binds this vascular endothelial growth factor and sucks it out of your retina. Blood vessels need VEGF to grow. So if you take the VEGF away, the blood vessels can't grow and they involute, they shrink. It's an incredible treatment. It is by far the biggest advance in ophthalmology in my career. The upside is it works great. The downside is it's a royal pain, because you have to have injections every month initially and then every 2 or 3 months. You're lucky that you don't have a lot of discomfort. There are people who, despite all the anesthetic we can put on the eye, still feel some of this, like pressure sensation. And psychologically, a lot of people, for whatever reason, don't like the idea of someone coming at you with a needle in your eye. And so it's a very unpleasant experience for some patients. Usually people kind of get accustomed to it, but I still have patients who do just tense up every time that they come in and they need an injection. So I don't think we're done yet with wet degeneration. I think there's going to be some more treatments coming down the pike, especially gene therapy. If we could make that antibody, make your cells, your own cells, make that antibody 24/7, you wouldn't need injections anymore. And that's in development right now, is to do gene therapy to eliminate the need for continuous injections with the same drug.
Okay.
Yep. I'm letting you guys pick who gets the microphone. So,
Have there been any major improvements in the treatment of retinal detachment?
yeah, retinal. So the question is, have there been improvements in the treatment of retinal detachment? Absolutely. There were 2 seminal advances that are fairly old now. The first was to do scleral buckling, which goes back to the 1950s, and that involves going outside the eye and actually putting a little silicone band around the eye to take the tension off the retina to allow it to reattach. And then in the 1980s and early 90s, the development of vitrectomy, which is a technique where you go into the eye and remove the jelly, the vitreous jelly, using very high-speed rotary cutters. We haven't had an equivalently big jump in technique, but the refinement of those 2 techniques, especially vitrectomy surgery has been remarkable over the last 20 years. When I was a resident in the 1990s, we used 19-gauge instruments. And if you've had an IV placed in the emergency room, it's usually a big 18 or 19-gauge, big needles. Now we can do a retinal detachment surgery with 27-gauge instrumentation. I mean, that's the size of a tuberculin syringe. So the holes are smaller, the surgery is much less traumatic, and the results are better. Overall anatomic success rate of getting a retina back onto someone's eye is about 95% at this point. So we can fix most detachments. If people wait before they see us and the retina's been detached for a week or two, we still have a hard time getting the vision back because the photoreceptors have died. And then it falls into the same category as macular degeneration, where you'll need a restorative technique to try to bring the vision back for people who have been out there. So if you do see a curtain coming up or down over your vision, don't say, oh, it might go away. You come and see us immediately, because the faster we get to the operating room, the better your vision's going to be.
I have been had my insurance with the University of Washington for about 25 years. But when I was diagnosed with macular degeneration, and it turned out to be the dry kind, and the shots didn't work, they gave me a list of people. They called me low vision, and gave me a list of people I could see, whom I did go to see one of these people. And the first thing I had to do was sign a paper that I would not try to return if any kind of merchandise that I bought from this guy.
Yep.
And anyway, I signed it because I was desperate. And he did make some glasses that didn't work at all. He was not an ophthalmologist. And they cost me $4,900, which they're just sitting in a drawer. And I wonder, is this the way that the UW treats its patients?
Well, I'll remind you, we didn't treat you that way. That was on the outside.
You gave me the name of this guy.
That I apologize for, and afterwards I do want to find out who that person is. So low vision is a real challenge, meaning people who have lost vision, and we're not talking about restoration with these techniques, but we're talking about assistive aids and things that magnify and so forth. We used to have a good service in town, which was called Sight Connections, and they were our low vision, King County low vision group. They had a wonderful optometrist. She did a great job. Sight Connections, this is a story of philanthropy gone wrong. They hitched their wagon to Value Village, the secondhand store. And Value Village had agreed to, give them a chunk of their proceeds as part of their business, so they could say that they're, serving the community with. And it turned out that they weren't really giving a chunk of their proceeds to Sight Connections. And when federal auditors came in, they basically shut down Value Village, and Sight Connection, our low vision service in King County, went bankrupt and went out of business in 2019. We did not have a low vision service. It takes actually quite a bit to set up that service and get all the equipment in that you need to demo for people and see if it works. And for a few years, no one was providing those services. And I suspect the name you got was because that was one of the few optometrists in town who was providing services. More recently, the Lighthouse for the Blind has picked that up, so down in Sodo, and they are now providing some low vision service. This is a huge problem. The economics of running a low vision service are disfavorable for almost all providers unless you go through these mercenary things of selling people devices that they may or may not find useful. We frankly can't afford to run a low vision service because we're a state organization, and it honestly loses revenue for us, and we can't subsidize it. We don't have a place to subsidize it. If anyone wanted to come in philanthropically and support our service, hallelujah. We would love to offer low vision. We just can't do it right now from a financial standpoint. So that's left the low vision community in a real lurch, and we recognize that. I wish we had a solution for it, but at this point we don't, other than to go back to the Lighthouse, which I do trust in terms of being a vendor. But yeah, there's mercenary folks out there, and I'm sorry that if we pointed you in that direction.
Well, I still feel abandoned.
What's the definition of low vision?
Generally, legal blindness in the U.S. is considered best corrected vision in your better eye worse than 20/200. Can't see the big E on the eye chart. Or a visual field less than 10 degrees. Either of those are considered legal blindness, and that's when we were talking about low vision.
Yes. You talked about something coming down or up and down in your eye. When I go out into the bright sunlight, one of my eyes seems to get a cloud on it. Is that the kind of thing you're talking about?
No, that's probably not a detachment. Detachments
Yeah.
are usually one way.
Yeah,
The curtain
okay,
comes down,
yeah.
it doesn't go up. But that could be a sign of some dry macular degeneration, possibly. One of the symptoms people get are difficulty going from bright to dark or dark to bright.
But it's only in one eye, and now looking here, I have no
Which
problem at all.
can happen. And so macular degeneration can be asymmetric. Glaucoma can be asymmetric, so you can have one eye involved and the other one not as involved. So I would get a good eye exam just to see what's going on there, because that's a concerning enough symptom. I would get it checked out.
You call it sci-fi, and you talk about how people in your network see how science has developed something in some field and then think about how to apply it. What percentage of the times when you think about those connections does it come through and prove to be worthwhile? I mean, it's pretty amazing to see.
Very, very, very rare, right? So the old Thomas Edison comment that success is, 99% perspiration and 1% inspiration. Most ideas are bad, and I have had more bad ideas than everyone else put together. But every once in a while, serendipity hits. And, my kids used to give me a hard time for how much I do go to meetings and travel. But that's where you find out about other things. And this whole small molecule came about at a FASEB, a Federation Society for Experimental Biology meeting in June of 2006 in Palm Desert. I don't know if you've ever been to Palm Desert in June. Not the season to visit, but it's the season you can get cheap hotel rooms, and so that's why they had the meeting there. And it was particularly miserable. It was over 110, and they say, oh, it's a dry heat. No, it was a monsoon. So it was 110 degrees and like 90% humidity. So we were trapped in the hotel, could not go outside, and I happened to be sitting next to a guy named Rich Kramer, who's a professor at Berkeley, and he was telling me about these small molecule photo switches he was working on in the brain. So he was using hippocampal slices of brain to test these things. I said, well, brain, you don't want light-induced epilepsy. That's not useful. Have you put it on the retina yet? And he said, well, we've thought about it, but we don't really have the technique for measuring the retina's activity. I said, I have that technique. Let's collaborate. And so we set up the collaboration, and here we are 16 years later, and we're in people. And, although that's slow, for science, that's pretty quick to go from the germ of an idea to, execution like that. So a lot of it is serendipity. A lot of it is having a very broad education and being prepared to see things. But you're exactly right, Ginny. A lot of what we do is we look for opportunities that are happening in other fields of science and say, how can we improve vision with that, whether it's stem cell or adaptive optics in imaging or these small molecule photo switches. And collaboration is key, and being in a great environment like University of Washington, where there's so many good scientists doing so much work in so many areas, really helps keep us at the forefront of what we do. All right, well, if no other questions, I'm happy to stick around for a while and answer individual questions. And again, Kathy and Michelle are here, and I will turn it back over to Ginny.
Well, thank you very much for coming. You certainly didn't disappoint. Thank you. And I want to say there's a sign-up sheet over here if you want to get information from them on a regular basis. And there's a booklet that describes some of what we heard about. Do you want to say something more about it, Michelle?
We have our ophthalmology annual report, which kind of shares a little bit of the information that Dr. Van Gelder just shared, and also some additional articles in there. And they're here for you. And if you would like to sign up for emails, we're happy to put you on our ophthalmology email list, so you'll get all the news and kind of the latest things that are coming out.
So thank you again, and when you come up with some more, just let us know so we can have you back. We certainly appreciate it so much.
Thank you.
So much.